right, so now that you guys have watched the conservation of energy video, let's actually work on some examples besides that one that we did in the video. So let's do basically just a whole bunch of examples, kind of get used to it and work through our steps and do all that good stuff. So my first example says that we have a grasshopper. So here's going to be my grasshopper, my beautiful drawing of the grasshopper. It's going to start off with some initial velocity v0 at some angle of theta, which is equal to 45 degrees relative to the horizontal. So in this case, he's going to jump, undergo projectile motion, and then what we know in this case then is that what he's going to reach some maximum height. So at this point, his maximum height then, called that h max, is going to be equal to 1 meter. So what we want to know in this case then is what is the initial velocity of the grasshopper to get him to be able to jump at a 45-degree angle to reach 1 meter. So let's go through our steps. So step number one is to draw. So here's my before picture, great. And then my after picture is when he's going to be at maximum height. Now, when he's at maximum height, we have to remember that even though the y portion of the velocity is equal to 0, it doesn't mean that all the velocity is equal to 0, because as we know from projectile motion 1,000 years ago now, that whatever initial velocity he had in the x direction will still be exactly the same velocity that he has in the x direction, because there is no acceleration in the x direction. Right? So what this means is that his final kinetic energy is not equal to 0. If I take the entirety of the kinetic energy, it's actually going to be 1/2 his mass times his final x velocity squared. So good. So in this case, there's my before, there's my after picture. Step number two, do we have any potential energies? In this case, yes, we have a change potential energy. That change is going to be gravitational potential energy. So good, we got that. Step number three, do we have any non-conservative forces? In this case, no, we don't have any non-conservative forces because we always ignore air resistance and all that kind of good stuff. So there's no friction or anything like that, which means that in this case, step number four, work done by the non-conservative force is simply equal to 0, which means that now we can apply step number 5, conservation of energy. So that says that our change in kinetic energy plus our change in specifically gravitational potential energy must be equal to the work done by the non-conservative force, which in this case is simply 0. Now, as we just said, the final kinetic energy is going to be 1/2 the mass times the x portion of velocity squared minus its initial, which is 1/2 mv0 squared. Now remember, kinetic energy, we don't care about direction. So all we care about is that he has a total amount of velocity of v0. We don't care what direction it happens to be. So that's why in this case, we're not going to have any cosines or sines or anything like that. Plus my final gravitational potential. Okay, so when it comes to gravitational potential, we can again arbitrarily define some point to be our 0 location because there's that ambiguity built into gravitational potential. So in this case, let's take that the y is equal to 0 location is the ground. So that means that his initial potential energy is 0, while the final potential energy is then simply equal to mgh max. So in this case, I'm going to get then a plus mgh max minus his initial is then all equal to 0. Now, in this case, all the masses are the same. Let's cancel those out. Right. So let's plug all this stuff in. So then I'm going to get a 1/2 vx squared minus v0 squared plus g times h max is then equal to 0. Now remember that vx though is the initial x, which means v initial x is simply equal to v initial times cosine of, in this case, 45 degrees. So when I square that, each one's going to have a v0 squared term. And remember that cosine of 45 degrees is square root of 2 over 2, which is 1 over the square root of 2. So if I square that, that becomes simply 1/2. So good. So this becomes then 1/2 v0 squared times 1/2 minus 1 plus gh max equals 0. Of course, 1/2 minus 1/2 is the same thing as negative 1/2. So I'm going to bring that term to the other side. So what I finally get then is that what 1/4 v0 squared is then equal to gh max, or finding my initial velocity. My initial velocity then is going to be equal to the square root of 4 times gh max. Plug in my numbers. In this case, what I find is that this works out to be 6.26 meters per second. Now, just a quick kind of summary of this guy. Number one here. We could have used kinematic equations to do this. We know the only force acting on this as it flies through the air is a gravitational force, which means that it has a constant acceleration because the acceleration due to gravity, in this case, is a constant acceleration. So we could have used kinematics, but in this case, since it's projectile motion, we would have to work with both the x direction and the y direction, use the y direction then to solve for the time, and then plug that into the x direction then to eventually get the initial velocity. But in this case, we don't have to worry about any of that stuff. All of that is simply built into the air, so we don't have to worry about components and directions and all that kind of good stuff. So it's actually much easier. Not too bad. So let's do another one. So this one says I have a block which is sliding on initially a frictionless surface, and that block has a mass of m, where m in this case is equal to 2 kilograms. And this surface down here again is frictionless, at least initially. And this thing's going to have an initial velocity to the right, v0, which is equal to 4 meters per second. So this guy's going to slide until eventually he runs into a spring. So here's my spring, which is attached to, say, a wall. And then underneath the spring, there's now a coefficient of kinetic friction. So that coefficient of kinetic friction then is equal to 0.8. And this guy has a spring constant K, which is equal to 10,000 newtons per meter. So that's a pretty stiff spring. So what's going to happen? So this is my, again, initial picture. So afterward, what's going to happen then is what? This guy's going to come here. It's going to be here. So what'll happen then is that the block will hit the spring and then compress the spring. So the spring then is going to be compressed. So here's my compression. Here then again is my distance at which this is acting, or my friction force. So here now is my mass of mass m. So what I want to know then is, given that this thing is initially at its equilibrium position, let's call that our x is equal to 0 location, what then is going to be the maximum compression? So let's call that simply d, where d then is going to be equal to the maximum compression. Now, what has to be true is that maximum compression, my block has to momentarily stop at maximum compression. So in this case, I know that my final kinetic energy has to be 0 for maximum compression. Because if it hasn't momentarily stopped, that means it's still going to be moving, so that won't be maximum compression. And then after maximum compression, it's just going to shoot back out in the opposite direction, because I'll turn all that spring potential then back into kinetic energy. So good. So here is my before picture. Here is my after picture. Again, this is simply my K value. So again, what I want to know then is what is next. So again, let's go through our steps. So step number 1 is done. So again, here's my initial picture. And then here's my final picture, right? Step number 2 then, do I have any potential energies? Well, in this case, I do have a gravitational potential energy, but more appropriately, my gravitational potential energy never changes because it never moves up or down. So in this case, my initial gravitational potential will be equal to my final gravitational potential energy. So in that case, my change is simply equal to 0. But I do have a spring. And my spring starts off in equilibrium and then gets compressed. So in this case, I do have a spring potential energy change. Now, initially, this thing has, let me color I haven't used it. That'll work, red. So initially, my spring is in its equilibrium position. Remember that spring potential energy is equal to 1/2 k times x squared, but x in this case is equal to the distance away from equilibrium. So since my spring is initially at an equilibrium, that means that my initial spring potential is simply equal to 0. Afterward, my final then spring potential energy then must be equal to simply 1/2 k times the distance it is compressed, which is what we're calling d squared. So I do have a change of potential energy, in this case, spring potential. Pardon me. Step number 3, do we have any non-conservative forces? In this case, the answer is yes, I have friction. So yes, friction. And then what is the work done by that? So the work done by my non-conservative force then is equal to my work done by my friction force, which is then equal to the friction force times the distance over which the friction has acted, which is the same as the compression distance d, since the friction starts underneath of the spring, times then cosine of the angle between the two. We'll call that the angle phi. Now, in this case, what I know is that my compression is, as I have drawn in this direction, so that is my displacement vector d pointing to the right. but my friction acting on my object is back in this direction, because it always is opposite the direction of motion, which means in this case, phi is simply equal to 180 degrees, and cosine of 180 is -1, so this becomes then minus f sub k times phi. Now, to get f sub k, we know again f sub k, based off of last exam, is mu sub k times the normal force. Right? So let's think about the forces that are acting on this guy. Well, we know we have gravitational force. Okay, it's going to be down in this direction, mg. And then we also have the normal force. My normal force would be up in this direction, my normal force. And since it's not accelerating in the y direction, that means then my normal force is simply then equal to mg. So in this case, I know this is going to be mu sub k mg. So let's plug that in. So this becomes minus mu sub k mg times. Good. So that's step number 4. Finally, step number 5 is apply conservation of energy. So let's do that. So I'm going to say my change in kinetic energy plus then my change in spring potential energy is then equal to the work done by the non-conservative force. So in this case, we know our final kinetic energy is 0 minus the initial, which is 1/2 mv initial squared, plus my final spring potential, which on the other page we already said was equal to 1/2 kd squared, minus my initial, which is 0, is then equal to the work done by the friction, which is minus mu sub k times mgd. From here, all I care about is what's d. So if I look at this thing, I can see, well, I would actually have to solve a quadratic. So let's make it look like a quadratic. So this becomes 1/2 kd squared minus, plus mu sub k mgd minus 1/2 mv initial squared is equal to 0. So from this, I would find d then is equal to minus b. So it's minus mu sub k mg plus or minus the square root of mu sub k squared m squared g squared minus 4 times a, which is 1/2 k, times c, which is minus 1/2 mv initial squared, all divided by 2 times a, which is 1/2 k. Now from here, this negative sign here cancels this negative sign, which means I have a positive sign in here, which means that this term here is greater than the left term, which means I can only then take the positive root. So taking the positive root, what I find in this case then is that this works out to be 0.055 meters, or that's equal to 5.5 centimeters. Now, let's talk about this problem just for a second. So notice this problem, there's no way we could actually use forces and kinematics to do this problem. And the reason for that is because we have a spring. So anytime we have a spring, we know the force of the spring is equal to what? K times x, at least that's the magnitude of the force, which means my acceleration then is going to be directly proportional to x, which means it's time dependent. Since I have a time dependent acceleration, that means we can't use kinematic equations because we know our only caveat for kinematic equations is that we have to have a constant acceleration. So no constant acceleration, no kinematics. So for this problem, there's absolutely no way we could do this. We could either then use the work kinetic energy theorem or conservation of energy, but conservation of energy is typically going to be easier than work kinetic energy theorem. So good. So let's talk about another problem. So let's get problem number 3 here. So this one says we have a quarter pipe, my quarter pipe, which then becomes a flat surface for a while. Good. So here's my flat surface. So what I know is here, this is point A. This is point B, which is at the bottom of the quarter pipe, where my quarter pipe has a radius of r, where r then is equal to 2 meters. Then from B to C, there's then a coefficient of kinetic friction, or my coefficient of kinetic friction then is equal to 0.25. And this has a distance of, let's call that distance d, which is then equal to 3 meters. Now where C is, C then, from the rest of this is frictionless. But then there's a spring at C, which goes the rest of the way. So what I'm going to do then is take a mass. So here's my mass, m, where m is equal to 1 kilogram, and then let that guy slide down until eventually it's going to then compress the spring. Okay? So eventually what's going to happen then is here again, my quarter pipe. There's all that. So there's my B, there's my A again. There's my point C. And then this guy is going to compress the spring. So that way, by the time it stops here, so this will be maximum compression, where again, this is my x is 0 location because that's an equilibrium. to now this location here. So this is going to be compressed by an amount of x, where x is equal to 0.2 meters. Okay. So what I want to know from all of this then is, what's the spring constant? Okay. So good. So let's talk about this one real quick. So for this one, notice that again, I can't use kinematics or forces for two reasons now. So number one, this region up here, which has the quarter pipe, has a non-constant acceleration because it's not an inclined plane, right? So it's a curved path, which means again, in this case, my acceleration will be time dependent. And then over here, that portion in gray, again, I have a spring, which we know means that the acceleration is proportional to x, which means it's also proportional to time, right? So basically, in this problem, there's, again, no way I can actually use forces or kinematic equations to actually be able to do this problem, at least not at this level. If I knew differential equations, I could actually do that, but in this case, I don't, so I can't do it. So great. So let's talk about our steps. So step number one, again, we drew our initial picture, we drew our final picture. Step number two, then, do we have any potential energy warping? More particularly, do we have any potential energy changes? In this case, I actually have two, right? So I have a change of height here, right? So going from A to B, so that means I have a gravitational potential energy. And then I also have a spring, which means I have a spring potential energy as well. So for this guy, again, for gravitational potential energy, we always wanted to define Ry is equal to 0 location. For this guy, the easiest place to define it is along that straight path going from B to C, which means that this guy is going to finish with 0 gravitational potential energy, but it is going to start off with a non-zero gravitational potential energy, which is simply mg times the height, but the height here is simply equal to the radius. For the spring, again, initially this guy starts off in his equilibrium position, which means the initial potential of the spring is going to be 0. But then down here, we know then that the final is then going to be 1/2 times k times x squared, where x again is just that compression distance. Step number 3, do I have any non-conservative forces? Well, in this case, the answer is yes. Again, there's friction from B to C. So what is my work done? Step number 4 by my non-conservative force. Well, that's going to be the work done by, again, the friction force. In this case, let's draw an intermediate picture here. So at this stage, we know, again, our displacement is going to be in this direction. With my displacement D, we know our friction force is going to be in opposite direction. So we call that our friction force in this direction. So this guy is going to be simply equal to the friction force times the distance times cosine of, again, 180 degrees. And it's the distance D because, again, the friction acts over the entirety of this distance between B and C. Again, cosine of 180 is -1, so this becomes minus my friction force times the distance. And again, we know our friction force is equal to mu sub k times the normal force. But again, in this case, since I have my gravitational force downward, I have my normal force upward, and there's no other forces in the y direction, is also not accelerating. That then tells me that's what my normal force is simply then equal to mg. Plug that back in. So this becomes then minus mu sub k mg. Good. Now, the next question is, well, how do we actually solve this problem? Now, it turns out there's a couple different ways we can solve this problem, but one way we could do it is we could split this up into sections, right? So I could do this section from A to B, call that section 1, and then we can find the velocity of the block at B. So we're going to find the velocity dv. Then going from B to C, let's call that then section 2. We then are going to have a slowing down of the block because there's a friction force taking away energy, converting it into thermal energy. So in this case, it's going to slow down going from B to C. So then we could use that to find then the velocity of the block at C. Then we can do that here. This small section here, which would then be section 3, where the block then comes to rest. So again, we have 0 velocity, but then the velocity then gets converted into potential energy. We could do it this way. So in this case, I would use conservation of energy in section 1, and then conservation of energy in section 2, and then conservation of energy in section 3, and then just paste them all together to then get the final answer. That's one way we can do it. Or we can do it the other way, which is what's called the short way, which means that we're just going to do the whole thing in one beautiful step and just not even have to worry about it. So in this case, I don't have to split it up. I can simply do everything going from the initial point here all the way to the final point and when it stops, and then I don't have to worry about any of the details in between. So let's actually do it that way. Now, I encourage you to do it the long way, breaking up the steps just to get extra practice on that. And if you do that, you can turn it in as a group assignment. I'll give you a point of extra credit for doing it that way. But again, you don't have to. So let's do the very short way. So again, conservation of energy, step number 5, then says the change in kinetic energy plus my change in potential, which in this case will be my gravitational potential, plus my change in potential, which is my spring potential, then is equal to the work done by the non-conservative force. So all I'm doing here is I'm splitting up that change in potential into the 2 types of potential, which is my gravitational plus my spring potential change. Now in this case, let's go back to our picture. We know the initial velocity of our block here is 0. We know the final velocity is also 0, which means the change in kinetic energy is then simply 0. So this term is just gone. For gravitational potential, as we said on the other page, we know that our final is going to be 0 minus my initial, which is mgr, plus then my final spring, which is 1/2 kx squared, minus my initial, which is 0, is then all equal to minus mu sub k mgd. Good. From all this, all we want is then the spring constant. So I'm just going to add this term to both sides and then multiply by 2 and divide by delta or x squared. So let's do that. Finally, get k then is going to be equal to 2mg. So I'm going to factor out that mg, r minus mu sub k d, all then divided by x squared. Plug in my numbers. What I should find in this case then is this works out to be about 612.5 newtons per meter. Now, let's do one more example. In this last example, I really like this example because it's a great example of how beautifully simple conservation of energy is versus using forces in kinematics. So let's talk about this. So in this case, I'm going to look at the extra credit problem from the previous exam. So on that one, what we had was what? An inclined plane. We had a mass that was up here, mass m, and then it slid starting from rest. So in this case, my initial velocity was equal to 0. It's going to slide some distance of x until it gets to this point. Okay. Once it gets to this point, then I'm going to draw this in green. So here's my mass. We're then going to pull on it with a string with a tension force in this direction, causing it then to slow down. So that way, by the time it gets to the bottom, where it has now gone a total distance of x prime, the final velocity then is equal to 0. Okay. Where the initial distance of travel plus the final distance of travel is equal to the entirety of the length of the plane, right? So the length of the hypotenuse. So here, what I want to know is, according to that problem, what's the tension? So notice what's happening here is I have actually 2 different accelerations, right? In the first section, this guy is accelerating down the plane because it is going to be speeding up until it reaches some velocity here. Let's call this intermediate velocity. Let me call that v prime, where v prime is going to be in this direction. And then it's going to slow down, which means that I'm going to apply some acceleration to it in the opposite direction. Call that a prime, until this guy is going to slow down. Okay. So a prime is being slowed down because of the tension. So I'm going to have to first find what a prime is to then get the tension. But to get a prime, I need to know what that velocity v prime is. And to get the velocity v prime, I need to know what the acceleration is first in the first section. Right? So basically what I'm going to have to do then, I'm going to break this up into sections. So my first section here is going to be here, where I'm going to have to find first that acceleration. So let's use forces. Let's see how this works. So here I'm going to draw my free body diagram. Right. So here I know I have mg downward. I have my normal force perpendicular to the surface, and that's it. Right. And then here I know that this guy is going to be accelerating down the plane, so it's going to be the direction of my acceleration. Close enough. Good. Now from here, let's fit in our coordinate system. So we want the x-axis to go in the direction then of my acceleration. Y is going to be perpendicular to that, my y direction. And then this guy then is going to be my angle of theta. So for this guy, since I only want the acceleration a, which only points in the x direction, then I'm just going to use the sum of the forces in the x direction since there's no friction. So I'd say some of the forces in my x direction are equal to ma. The only force in that direction is going to be mg sine of theta, which is then equal to ma. So in this case, my m's are going to cancel. So that tells me that my initial acceleration is just g sine theta. So this is my acceleration of a. From a, I can then find v prime. Now for v prime, what I know is the distance at which it travels, x. I know the initial velocity. I'm looking for the final velocity. So which one of my kinematic equations works the best? Well, that's going to be kinematic equation number 3. So from kinematic equation number 3, I can then say that's what my final velocity, v prime squared, is equal to my initial velocity, the initial, which we know is 0, plus 2 times the acceleration times my displacement, which is simply x. So this tells me then that v prime squared is then going to be equal to 2 times g times sine of theta times the distance x. Now, I'm not going to bother solving for v prime because I'm going to need v prime squared in just a minute anyways, but I'm just going to leave it this way. Great. So now let's look at section 2. So in section 2, now what I know is that this is my initial velocity for section 2, and I know my final velocity is going to be 0. I know the distance at which it travels, so from that, I'm going to find my acceleration a prime. So for that, we can again use our third kinematic equation. So let's look at section 2. So for section 2, we can then say that our final velocity squared, which is 0 squared, is equal to my initial velocity, which is v prime squared, minus then 2 times my acceleration a prime times the distance x prime. Pardon me. So from here, a prime then is going to be equal to my velocity v prime squared divided by 2 times x prime. Now let's put in v prime squared. So this then becomes 2 times g times sine of theta times x divided by x prime. Or actually 2x prime. The 2's are going to cancel. Good. So this thing finally becomes g sine theta x divided by x prime. Great. Now what? So now we know the acceleration a prime, and now we can go back to our forces and look at, again, another free body diagram. So let's do that. So from here, I now have that's what? We still have mg downward. So here's mg. We still have our normal force in this direction. But now we have our tension force, which is now up the plane. And we know our acceleration, a prime, is also up the plane. Good. So from here, again, we would choose our x-axis to point along the direction of a prime. So it's going to be up the plane this time. Y-axis perpendicular, and then our theta is between mg and the y-axis. So again, from here, since I want my tension, I only care about the sum of the forces in the x direction. So I'd say the sum of the forces in the x direction then are going to be equal to ma prime. So here, t is going to be positive, minus then mg sine of theta is now equal to ma prime, which means if I use this to solve for t then is going to be equal to m times a prime plus g sine of theta. Now plugging in what a prime is, so this becomes m times g sine theta times then x. Sure I got that right. Yeah, x over x prime. There we go. X over x prime plus 1. Or find a common denominator. So this becomes mg sine of theta times then x plus x prime over x prime. But going back to our original picture, x plus x prime is the same thing as L. So this thing finally just becomes mg sine of theta times L divided by x prime. So this then is my tension. Oh, that was a lot of work. Okay, so notice in this problem, I had to do multiple things. So again, going back to section number 1. So in section number 1, first I had to find the acceleration. So I had to use forces. Then I had to find the velocity v prime. So then I had to use kinematics. Then in section 2, I had to find the acceleration using kinematics. So from here, I can then use kinematics to solve for a prime. And then to finally get the force, going back to section 2, and then I have to use the sum of the forces then to get the tension. A lot of steps have to happen. Now, Let's do the same problem, but this time using conservation of energy and compare the two. So let's go back to our original picture. So again, here's my inclined plane. I know this is my angle of theta. I know that this whole distance across here is my distance of L. My block again is going to start off here with my initial velocity equal to 0. It's going to finish down here with my final velocity equal to 0. And then at this point here, which is some distance of x, this is my distance of x prime, I'm then going to apply that tension force up the plane in this case. Right? Super. So now let's use conservation of energy. Now, just like the previous problem, we can break this up into multiple sections. So first we could find the velocity at x, and then use that and use the distance of x prime and then find it that way. So we can break it up into sections, but we're going to do the same thing we did in the last one and just say, forget all about that. And we're just going to do the whole thing all together. We're going to do the short way. Now, from here, we then again are going to apply our steps. So our steps are done. Step number 1, we drew the before picture, we drew the after picture. So that thing again has tension acting on it up in this direction. Great. Step number 2, do we have any changes of energy? The answer is yes, we have a change of gravitational potential energy. So we know this thing starts off up at the top, ends at the bottom. So let's choose the bottom to again be y is equal to 0, so that initially this thing starts off with y initial worth of energy, right? Or at least of height. Now, since we know L and since we know sine of theta, then we can rewrite y initial here. So y initial is then simply equal to L sine of theta. So that means that my initial gravitational potential energy is equal to mgl sine of theta. And my final then is just going to be 0. So step number 3, do we have a work done by nonconservative force? The answer to that is actually yes. And as we talked about in class and in the video, hopefully I talked about this. In this case, it's actually the tension is actually the nonconservative force. And I know that's because in this case, the tension is taking energy away from the system, causing it to not have the velocity that it should have by the time it gets to the bottom of the plane. Right. So what it should have is that the velocity at the bottom of the plane should just be the square root of m, right? M's a great example. So this is just going to be g times the height, right? In this case, that's going to be y initial, or 2 times that. But here, it doesn't have this velocity and actually has 0, which means that something took energy away from the system, and that was actually tension. Great. So then what is the work done by the nonconservative force? That then is going to be equal to the work done by the tension, which is going to be equal to tension times my displacement. In this case, my displacement will be down the plane, but if the tension is only acting on the distance of x prime, it's again going to be times x prime, times then cosine of the angle between the two. Now, in this case, since the displacement is down the plane, but the tension is up the plane, that means my angle then is going to be 180 degrees. So that means my work done by my tension is minus t times then x prime. So let's now do step number 5, apply conservation of energy. So we get our change in gravitational potential energy plus our kinetic energy is equal to the work done by the nonconservative force. Now, in this case, since the initial velocity and the final velocity are both 0, that means my change in kinetic energy is 0. Right. So it's going to be my final gravitational potential, which is 0, minus my initial, which is mgl sine of theta, is then equal to minus t times x prime. Then these are going to both become positive. I'm going to divide both sides by d prime. So what I finally get then is that my tension is simply equal to mgl sine of theta divided by x prime. Comparing that to then what it took me to do forces, this solution then is exactly the same. So notice here that I did this entire problem using energy in simply 2 steps, as opposed to all kinds of steps using forces and kinematic equations, right? So again, I really like this problem because this is a great problem that illustrates the power of using conservation of energy. Because again, I don't care about drawing free body diagrams. I don't care about directions that things are moving. I don't care about using kinematics, which again are all vectorial quantities, just like forces are vectorial quantities. Everything here is a scalar. All I care about is how this thing starts, how it finishes, and none of the details in between the two. So we can actually do highly complicated questions in like 2 lines. That's it. as opposed to doing forces and kinematic equations where we have to do a lot, assuming we can even use kinematic equations, because if I don't have a constant acceleration, then I can't use this at all anyway. So this is one of the beautiful parts then about conservation of energy. We can do these things. Now, the trick in this problem, though, is just to realize and to recognize that the tension force is actually the, pardon me, the tension force is the non-conservative force in this case. So if I didn't recognize that, I wouldn't be able to really do this problem. So, but once I realize that that is a non-conservative force, then I can easily do this problem in 2 steps as opposed to all the steps we did before. So let's quickly then talk about when we can use conservation of energy and when we can't. Or when should you use, let's do it that way. So an automatic giveaway that you should use conservation of energy is when you're looking for a velocity. Anytime that you see that all you care about is what's the velocity or speed, like for example, how fast is it going when it reaches the bottom of the plane, or how fast is it going when it has fallen a certain distance, you should automatically start thinking about conservation of energy. Don't fool around with forces, don't fool around with kinematics, because everything about that is embedded directly inside of this conservation of energy. Step number 2, changes of height. So anytime I see a change of height, again, I'm just thinking about gravitational potential energy, and then I have, but conservation of energy automatically has that built inside of it, so I just don't even have to worry about it. So in this case, again, don't think about forces, don't think about kinematic equations. Whenever you see a change of velocity or a change of height, automatically you should think about starting with conservation of energy and then just moving on. The third one is whenever a spring is involved. If I have springs, automatically conservation of energy. So when shouldn't I use? So we shouldn't use conservation of energy when what? 1, you're looking for an acceleration. Reason for that is because, well, obviously the work kinetic energy theorem as well as conservation of energy do not involve directly the acceleration, especially conservation of energy. So conservation of energy, it has velocity. So I could technically find the velocity and then take the derivative of the velocity to get the acceleration. But typically, if I see something asking for an acceleration, what I want to use here then is, so automatically I want to think about if I have an acceleration to think about. Number 2 is anytime I'm looking for forces. Now, I know in a previous problem, we actually just found a force using conservation of energy, but it doesn't always work. At least it's not always helpful. So in this case, it's a lot easier than to just go directly to forces. So whenever I want forces, then I just want to use typically forces and then use some of the forces Newton's second. So these are the times when I don't necessarily want to use it. Again, I can use it, I can find an acceleration, but I'd have to find the velocity in general first and then take the derivative of that to be able to find then the actual acceleration. So it's just a lot easier than to just use forces in this case. When can we absolutely not use? So basically, when can I never use conservation of energy? So I can pretty much never use conservation of energy in projectile motion, at least the horizontal portion of projectile. Horizontal projectile. So why is that? Well, we know that what conservation of energy has a delta UG term, which deals with height, but there's nothing that we know of that actually has horizontal distance except for something like friction, right? So in friction, so if I was looking at, for example, the work done by the non-conservative force equals friction force, and this is going to be the friction force times some horizontal distance, x, times cosine of the angle between the two, right? Now, but in projectile motion, we always ignore things like air resistance. So there is no x component with inside of here because there is no work done by a non-conservative of force, which means in this case, there's nothing within inside of conservation of energy which would give me anything about horizontal. So this is one place where conservation of energy will unfortunately fail. So it's just going to automatically fail. I won't be able to actually find anything about that. So in this case, unfortunately, you would have to use specifically kinematic equations for projectile motion, working with both your x direction and your y direction, just to make sure that you actually can find that horizontal range that this particle undergoes. Unfortunately, conservation of energy won't do anything for you when it comes to horizontal distance. So that's pretty much the only place I can really think of that will always pretty much fail in conservation of energy. So other than that, I mean, you could pretty much apply conservation of energy to anything, even if you want an acceleration to be technical, but typically in that case, you want to typically go with forces. But for the most part, anytime you see a change in velocity or a change in height or a spring, your brain should automatically start thinking about conservation of energy. So what this means is what? When you're doing your homework or you're getting ready for the exam or you're sitting there in the exam and you see some question that says, what's the velocity after this thing has moved, I don't know, 25 meters, then automatically, you know, start with conservation of energy and just proceed. So now you don't have to think about using forces and kinematics and all those things. And then even if you can, and then sit there and think, can I even use conservation of, or can I even use forces because do I have a non-constant acceleration or not? In this case, again, it doesn't care. So automatically just start thinking about that. Or again, a change of height or a spring, automatically think about using conservation.